So shall we start it now? Hello, please type in the chat box if we can start. You may type Y in the chat box if everything is tested fine.
10 मिनट तक बैठना मैम कुछ ना कुछ पूछता।
अच्छा हाँ
स्टार्टिंग में बीच में भी बैठा है मोबाइल में ना कॉल करता है ठीक है वो जैसे आ जाएंगे।
अब यहाँ है ना अब
स्टार्ट करेंगे
अब स्टार्ट करेंगे
यस ओके वो तो दिक्कत है। अब शाम को मैम को ये प्रेजेंटर बनाने की बोलेंगे।
So what we have discussed yesterday, we have discussed what is the diode, what is Schottky diode on the energy band diagram, how can we work with these things we have already done. Now let's take the next one in the same series, and I'm just revising just for your readiness, and you can be on the same page. I'm just going to revise what we have covered yesterday. So we have covered, first of all, we have covered the diode. In the diode, this is the IV characteristics of the diode. You can say this is going in the forward direction. The diode is going in the forward direction. The switch becomes on. Here the switch is becoming on. Right? This is the practical application. Another thing is, this is the actual diode. Actual diode which we will be getting in the experimental results. Here, the upper side of the axis, this is milliamperes. While lower side it is micro or nanoamperes. Please make a note of this. We have to have diode voltage towards this and the diode current on the y-axis. There are two variables. Dependent variable is ID, while independent variable is VD. Right? In the reverse bias, you can see this is negligibly small amount of current is going to flow. In case of Zener diode, this is the Zener breakdown. After which we will be using this in voltage regulation. And in case of avalanche breakdown, this is actually the avalanche breakdown. Okay, so avalanche breakdown is to be avoided. There is PIV rating. So that PIV rating is nothing but this breakdown voltage. This PIV rating we need to avoid. Okay, in the reverse bias, we have to make sure that we are not having much more reverse bias than whatever at one is the piece for what it says. You can see this current is exponentially growing. Here it is growing exponentially, right? There is a curve. This is the curve, right? I am putting it by arrow. This is the curve, which we got it from the expression we had I0 Is into exponent of Vd upon Vt minus 1. From this expression we got it, right? But in the piecewise linear model, we will understand that the diode is not having such kind of behavior. Instead of that, the diode is having the behavior that it is the straight line, not like this, after which it is going to increase. So everything will be and then it is going like this. So every equation here in the where we are talking about this, where we are talking about this region or this region or this region, everything all by arrows I have represented. So all these can be expressed with the help of straight line equation. What is the standard equation of straight line? Y is equal to mx plus c. That is the equation in this integration format. And the standard equation becomes like ax plus bx plus c is equal to 0. That's the standard equation. So it means we will be representing every line over here in terms of the straight line. So we call this as piecewise linear model. Piecewise means there are multiple pieces, like this is one piece. Then the next one is the other one. This is number 2 piece linear. This is third one where it is seen off. This is third one, and this is the breakdown region. That is also the piece 4. So are linear actually, the pieces in the IV characteristics of the diode. We have to take a note of it. Okay. Another thing is ideal diode. In the diode, when we are teaching to the first year basic electronics, those who are from non-engineering branches or the first year student, we have to make sure that the learning should happen. We are not going to impose, okay, you learn this, there is some current potential and all these things, because maybe in future it is not being used so much. For example, in electrical engineering, we are talking about 220 volt or somewhat like that. In mechanical also, we are talking a little bit higher voltages if it is required by the motor or like fan or something like that. So it means the 0.7 volt or 0.3 volt, which actually was the minimum required voltage to turn the diode on. That is negligibly small, right? So we can omit that portion and let us take the theory of the ideal diode. So in the ideal diode, it is a good practice to make understand the non-electronics or non-electrical branch engineers to study the ideal diode characteristics that helps them to uh, solve a number of examples. So how the ideal diode will be working, we will be taking that if this is lesser than this, then it is 0. If it is just greater than 0 voltage, we are going to make it, the current is going to increase. So that's the ideal characteristics of the diode, and they will just take care if it is the voltage applied to the diode is lesser than 0, means the diode is off, the switch is off. And if it is a little greater than 0, it means the diode is on. The switch of the diode is on and the current will be determined. This is the current on the y-axis. That is being determined by the external resistance. I told you that there is a safety resistance, right? So this current has determined with the so whatever we are going to do is to determine what is the current. Okay. Say voltage R is less than R plus RD. RD is the resistance offered by the diode. So in the reverse bias condition, what is your RD? Infinity. So V upon R plus RD becomes 0 in the reverse bias. So this becomes 0. We'll just apply the simple KVL. Simple KVL we have to apply. So this is 0 current. And when we are taking it forward bias, in the forward bias, how much the resistance offered by the diode is? We are expecting 0. For the ideal diode, we will expect that the resistance offered by the diode is 0. RD is equal to 0 in the forward bias. But it is not exactly 0. Practically, this value is somewhat around like 20, 24, 25 ohms. Practically, this value we will be having for the diode, right? So this R is, let's say, 1 kilo or something. It means I am getting the current in terms of milliamperes. For electronic applications, the typical amount of the voltage ranges few volts, right? So the current is seen in terms of milliamps for electronics applications and the physics-based sensors and all these things. The current, standard current, is in milliamps. While for electrical applications, the current goes in amperes. So please make a note what is your application. Depending on that, you have to decide that which emitter mode you have to select. Yeah. So this was the simple diode, practical piecewise linear model, and the ideal diode we have discussed. And yes, heterojunction we have discussed yesterday. After that, we discussed the Schottky diode, and in this, how the band diagrams are bending for the metal and semiconductor junction, how it is going to make it P-type and N-type. For example, you can see this is less N-type because the N is shifted upside, while this is little bit more N-type at the surface because the conduction band is going to shift towards EF. That is the Fermi level, right? These will be the characteristics. There is a characteristic difference in the Schottky and the simple diode. So the red line is your Schottky diode. The Schottky diode is very fast because metallic junction is there. So there is nothing to hold on. The charge recovery time is reduced. And if the charge recovery time is reduced, it means it is win-win situation for you. You can make it used for the fast applications, very fast frequency applications, switching applications, you may use that. Next one was the Jenner breakdown and avalanche breakdown. So these are the characteristics of the simple diode versus the Jenner breakdown. So we have to focus on the reverse bias condition. Somewhere here you will be having your VZ voltage, and you can see the avalanche breakdown will be having the PIV, peak inverse voltage. Or it comes with the breakdown voltage. So so we have to avoid. This is the red zone. We are not going to reach into it because this is the dangerous for the device health. We can expect that the device is not working as normal after reaching into this region. So we have to avoid that. But yes, this is the good situation. Zener breakdown is used for the voltage regulation, right? So these things we have covered yesterday. Now let us cover the next topic, Zener diode as voltage regulator. So what is voltage regulator? See, we have the supply voltage. Some supply is coming. In our households, the most of the time the supply we are getting is the AC supply with 230 volts and 50 hertz. So it means it is going to vary with respect to time. It is going to vary like this. It is a sinusoidal wave. But for example, I want to charge my laptop. So what I need 12 volt DC supply, or I want to charge my let's say this phone. So I need a standard power supply 5 volt, right? Or let's say I am going to take the electrical applications like fan is there, freeze is there, motor is there, all these things I am going to take. But sometimes you might have seen there are fluctuations in the amplitude. Instead of 240, let's say it is going to get up mostly when the weather conditions are not really good. So it is going to shoot up. So if the amplitude is more, it means the current flowing through this is going to increase. Simple Ohm's law, I is equal to V by whatever the total resistance, right? So I is getting increased if V input is getting increased. In that, if I have a rating, I have a particular rating because I have presumed that all the input signals will not be volts are necessary. So in that case, my device is not able to clear the increased current. And if this is so, it means what is going to happen? There is the possibility that my device is getting damaged because of the I square RT heat dissipation. There is the heat dissipation. I square RT. That's the heat dissipation. You might have heard it from that, okay, my fridge is burned, my TV is burned because of the switching power supply disturbance was there. So all these things actually are basically because of this component. Because our resistance offered by that is fixed, time taken is also fixed, and there is a switching in the I because the switching in the input voltage was going to happen. Which we need some regulator. We have to apply some way that we are going to make sure that our load will not have more than this voltage value. For example, I'm going to okay, it should not have beyond the 230 volts, right? So if it is going to come beyond 230 volts, this is active and it is going to stop. So that is the voltage regulation. So voltage regulation is of two types. One is the line regulation, and one is the load regulation. Line regulation the supply is going to vary in line. We have to deal with the appliance, right? This regulation. In the line regulation, we have the load which is fixed. For example, my fridge is there, so fridge load offered. We are offering, we are representing any anything else, we are going to represent by the effective impedance. So here it has been represented as RM, right? And Vs is the supply voltage over here. So that supply voltage is varying. R, the safety resistance R1, that is fixed, right? So in this particular, if I want to figure out that what will be the current in IL, how I am going to determine? कैसे determine करेंगे? How I can determine that? Can I apply KVL directly? So here, this is what we can offer. See, load voltage is equal to VZ voltage. In case of what? This is VZ voltage if your input voltage was more than your VZ voltage, right? If the Zener diode is on, then the load voltage is your VZ voltage. So Zener diode is on in two conditions. See, look at the Zener diode characteristics. Zener diode characteristics were somewhat like this. In the forward bias, it is simple diode. Okay. Reverse bias, it is 0 up to some value, and after that the current is limited by the circuit. Right. So it means Zener diode is on. If we are talking about reverse bias, it means we are talking about this region. Right. So here VL is equal to VJ. If it is in forward bias, if I am taking bidirectional power supply, which is like positive volts and negative also. Although in this particular case we have taken DC supply, we are going to offer the regulation for the DC supply, but the same is applicable for the AC supply also. So let's take the DC point of view. From DC point of view, we have reversed biased it. So it means from here to here, whatever the input is there, that is directly appearing at the output because through whatever the KVL is. There is resistance division rule. The voltage has been divided into R1 and RL, both of the resistances, that we can represent in this way. RL upon R1 plus RL. This is, see, total current will be Vs upon R1 plus RL. So total the voltage across the load will be VL is equal to Vs RL upon R1 plus RL. And Vs is nothing but this one. Vi minimum, it's been referred. So this is before this means this off region. This current is in this off region. This is the off region. So this is the current over here. This is the VL over here. What if we are going to increase this particular voltage? So for this particular case, if I want to find out what can be the Vi minimum, so we will make it like just cross multiply this Vz into Rs plus RL divided by R. So from this formula I am going to get Vi minimum. This Vi minimum is actually the load voltage, right? So now I have to, this is the input voltage and V is the load voltage, right? And this was the Zener diode on condition. Now we are going to fix RL. In that case, Vz upon RL is the IL at the output. Once the input is going beyond Vz, it means Vz is the only load at the output and RL is across the load. So Vz upon RL is IL. That's what IL is, load current. From this, there was a total current formula with R1 and RL. So we will determine what is the IZ current. IZ current should not go beyond whatever the Zener diode ratings are there. When you will look into the Zener diode data set, you will find out that there is a rating given by the manufacturer about how much maximum current and maximum power dissipation can be tolerated by that Zener device. So you have to make sure your IZ maximum current should not go beyond that, and the power is nothing but Vz into Iz. Vz is fixed, right? So we have to make sure about that. So look at this. This is your the case where Vi, the input voltage is lesser than Vz. In that case, the VO is equal to given by the formula. Let me write the formula. So the formula is input voltage Vs into RL upon R1 plus RL. And if this is greater than that, what is going to happen? Greater than that means the load is limiting. Load is having Vz only. Right? So where the access current is going to go? The access current is going to go into the resistance R1. And this access current can be determined with the help of input voltage minus Vz divided by R1. This is the access current, total current, let's say Is, supplied by Is. This Is is further divided into two parts. Iz and second part is IL. So Is is equal to IL plus Iz. When Vin was lesser at that time, this current was not going into this because this was off. Iz was 0. Right? But now the Vs value is more than that, so in the reverse bias we have crossed the Vz. So it means some certain amount of current is going into this, but we have to make sure that this current is not going to increase. So basically the current in Iz is going to increase. And that Iz, with the Iz value from here, it can be taken up. Iz is equal to Is minus IL. Right? So whatever excess current is there, that is flowing through generator. Why it is going to contributing to input IL? If you have any clue, please type in the chat box. Why it is not going into IL instead of Iz? Excess amount of current supplied from the supply. Why it is not going into Zener? Load voltage. Why it is not contributing to the IL? Yes, please type in the chat box if you have any clue. So basically, see, whenever this is in the Zener domain, right? So it means the resistance offered by this is approximately 0 because it is working like a constant voltage device. So you can replace it by the constant voltage, that is nothing but Vz, and series connected resistance. But the resistance offered is Zener diode Rz is equal to 0 in the Zener mode. There is no resistance offered. That's what you might have seen. There is a constant current in the IV characteristics of the Zener diode. Right? So basically, the excess amount of current will, if there are two things to follow, so the excess amount of current will always follow the lowest resistance part. And in this, the lowest resistance is this much. In the Zener domain, the lowest resistance was this much. That's why the current is contributed towards the Zener part, and it is not contributing to IL. So Iz actually is decided by our so maximum possible, whatever maximum rating of Iz is given to you. And this is the way we will be deciding that what can be my Iz. And from there we can figure out what can be my V. Next one is the load regulation. Previous was the case when we were varying the input. In this case, we are going to vary the output. Load regulation means we are going to regulate the load. In previous case, we were going to regulate the power supply. So in this case, this is fixed, R1 and Vs are fixed, and now load is going to vary. If load is going to vary, so we have to find out what can be the minimum load resistance. Because the load resistance, if it is being changed, it means there is a change in the current supply, right? And with the help of that, we have to figure out how it is going to change the things. So here the input voltage is constant, and it is too small a load resistance RL. that it will result VTH is less than VZ and Zener diode will become off. If it's too less, then it will become off. So we have to determine RL minimum with the help of this formula, because load voltage is nothing but VZ voltage, just like the previous case. And just like the previous case, we will be having RL upon RL plus RS into VI minimum, input minimum will be having. With the help of this formula, we can figure out what will be the RL minimum. So VZ into RS upon VI minus VZ, input voltage minus VZ voltage. Here input and VZ, both of these are constant. That's what we can determine the RL. And likewise, the IL, maximum amount of current, how much it can flow, we can determine with the help of that. See, if the load resistance is minimum, it means the current flowing through can be maximum possible, because the voltage VZ is fixed, right? So if voltage is fixed, it is the product of IL into RL. So if your RL is minimum, can I say RL is decreasing? It means the current IL is increasing. So if some of your device there, that device, how much current it can withstand with, there is a range of that. So in order to determine that, we have to find out what is the maximum. So with the help of RL minimum, we can determine this IL maximum. So if you have any questions so far, please let me know. Otherwise, we will move to the next topic. Do you have any questions so far? Please type in the chat box Y or N. N for no, Y for yes. No questions? Am I audible? Please type in the chat box something, at least you have to say. Okay, so now let's come to the next topic. So I think it is very easy, that's what you are not having any doubts. So let me make it a little bit faster so that we can cover the diode applications little in a little more. So I have given you the idea that the diode can be ideal diode, where more than 0 means the diode is on, less than 0 means the diode is off. That's the idea for the ideal diode. That you can teach to the non-electronics electrical people, because most of the time they actually require that only. So they don't really understand, and in fact they are not interested to understand that what should be the cutting potential, how it matters and all. But since all of us are electronics, electrical and from physics background, so for us it is important to understand, and being a teacher, it is really very important to understand how the diode actually is going to work. So in this half-wave rectifier, I have used the actual diode and with rectification. So there is AC input power supply. This AC input power supply is coming to here. This is your VS. So this VS waveform is shown over here. It is having minus Vmax and plus Vmax. Wait a minute, please. Yes, sorry. So there was a call. I have some official duties, so regarding to that there was some call. Thank you so much for your patience. So basically this is the input, and what we have at the output, this is a simple diode. This is the load resistance. So first of all, we are not talking about this capacitance. Forget about this capacitance first of all. So this diode, according to our piecewise linear model, ideal diode model. So what ideal diode says that in the forward bias you have the current which is limited by the resistance, and in the reverse bias you are having the zero current through the diode. So whenever the positive cycle from here to here is there, it means this is more than zero. So it means this is coming directly to the load resistance. And this is the output. You can see over here the dotted line. This is the output which is appearing at the load resistance. Okay, this is what it is. Now after this, whenever there is a negative cycle is seen, this is the negative cycle. So in the negative cycle, can I say that this is my positive, this is my negative? So this is the negative cycle. In this negative cycle, just see the polarity. So this comes like positive towards the negative side of the diode. So diode is having P type this and N type this. I told you the forward bias is when this is P is connected to the forward bias, P is connected to positive and N is connected to negative. But in this case, in the negative cycle, this positive is connected to negative also, right? So it means it is reverse bias. So reverse bias means this region we are talking about. So how much is the current offered by the diode? It is zero. It is open circuit kind of. So we can remove the diode from here. So the diode is removed from here. So the current cannot flow in the open circuit. So that's why the output will be zero. I is zero. So I into RL. What will be getting? This current becomes 0, and because I into RL, that's the voltage becomes 0. So output voltage will follow this route. It is like this wave, then this, and then after this, like this you will be following. So I hope you got this pattern, right? Now let's come to the actual thing. So what is the actual thing? We are talking about V gamma. So V gamma is 0.7. What I told that this is opposing the forward bias condition. So replace the diode with the we talk the diode the protected diode can be replaced with the diode must express oppose that oppose. Yeah, in this case, replace this diode with this combination, and this was V maximum, right? So up to 0.7 volt means this has to go from here to up to that the diode is not on. After that the diode is on. So how much it is? Can I write it like V in minus 0.7? That's the voltage which is actually going through means put this with the diode on. Right? After that, this is to pick up making on that things is broke because it is the current of good current is flowing. So this means this access voltage and you can just apply your case and we the access voltage V minus 0.7, which was nothing but the battery. So you can KVL. So there will be two routes for the KVL. First one you will discuss about this. You will write case 1 that this is a positive cycle. Then you will write case 2. In the positive cycle you will determine whether it is in or just write two cases. One is V in is greater than V gamma. I am going to take it V gamma because V gamma is the fitting potential that is varying for depending on what type of diode you are going to take. So if it is greater than that, that will be somewhere here. If greater than that, it means diode is on. And if diode is on, it means the current takes this path and the complete voltage, because there is no voltage drop over here whenever diode is on, so you can make it like short circuit. And this will be the output actually is going to appear over here, right? So complete V is after this is going to appear over here, but there was volt over here. So basically the output becomes V in minus V gamma in the forward bias, right? In V in is lesser than V gamma case, this is the case that the input is lesser than this. So I am making it red type. So in this revision the diode is off. Diode is off, it means this was not connected. So I was 0 and because of that we are getting this. So in this particular case the O region will be a little bit greater than the on region because the 0.7 is the positive voltage. By that time the diode is not on. So when you will take into consideration the practical, you will find that this is the output waveform when you are choosing the same zero axis at the y-axis and x-axis, you will find that the output waveform is not superimposing completely the positive cycle, but the output waveform is a little lesser as compared to the input waveform, and that less amount is actually at every place you are having V down. So it will look like this on your CRO or VSO. The output waveform will be this, and this gap is nothing but your V gamma. Everywhere this gap is V gamma. Okay. Now let's come to the next one. What is the utilization? So basically the half-wave rectifier is the one step towards the AC to DC conversion. So AC vortices we are having at homes, but for example, if I talk about the battery or let's say laptop or this it can be desktop or can be phone. So these are working on DC, right? We have to charge them with some DC source. So it means I have to convert the AC which is available at my household to DC, right? So this DC, how it is converted, the half-wave rectifier is the first step for that. So first, it is converted into this half cycle that is positive. DC is what? The average value. Whatever signal is there, the average value of that is represented by DC. So what is the average value of this? Can you type in the chat box the average value, V average for this? Input signal is there. That's the sinusoidal signal. What is the V average value? Please type in the chat box. V average value for the first input waveform, what it will be, please type in the chat box. Can you hear me? Yeah. So 0, very good. Push, it is correct answer, 0. And what is the average value of this? It is non-zero. Let's have this is non-zero. So it means it is better. We are one step towards that. But it is varying from this to this. Approximately 0 to V maximum minus V gamma. Exactly to be precise, what will be the peak? V maximum minus V gamma is the peak. Right? So it means we cannot say that this is the DC. So what we have to do, we have to filter out, and this is the capacitor filter we are going to apply. So when we are going to put this filter, the way actually at the input, this capacitor is getting charged. So it is getting started over here. This is going to charge the capacitor. Now the capacitor has charged over here. When this is charged over here, this is working like a battery. This is V maximum minus V gamma. V max minus V gamma. So can I say my input voltage, this was the V max, and because of this minus V gamma, that was appearing across this. That was the maximum possible. V max minus V gamma was the maximum possible. And my battery has already, my capacitor has already charged to that value. Now whatever value, let's say I have here or somewhere here, every value is lesser than this particular value. So it means left side, whatever you will be getting, that is definitely lesser than your VC value. VC is the capacitor value. So it means what is going to happen? It means the diode is not on. If the diode is not on, what is going to happen? This is going to discharge through this resistance, and we will get some voltage at the load. So what will be that voltage? This is going to discharge, and when it is discharged enough and the input is crossing the VC value, it is again going to charge. And after this, the diode is going to become off. So in this particular region, the next region, again the capacitor is going to discharge through the resistance. And in such case, we have this particular thing where the diode is on. Let me make it a little bit more clear. So this red line is the diode on, here to here, everywhere. This is the diode on condition. And whatever the linear type of thing we are looking into, let me make the different color. This line is actually the diode off condition, where the capacitor is discharged, and capacitor we are going to take the output across this RL parallel combination. So whatever the discharging is going to happen through the capacitor, that is actually observed at the output. So now let's have a look at this. Previously we were talking about from this to this. That was having V maximum and V minimum ratio. That was those were very far apart. But now what we have, we are going to have it lesser domain. So this is the V minimum and this is the V output maximum. So this is better as compared to the previous case. And if you find out DC of this, it means you are going to find out the average of this. So average of this will look somewhere here. So it means it is much far better as compared to the previous one. Okay. So now we can say, yeah, this is Schwartz DC. So in this way we will be converting it. But yes, there are some flaws in this, that this is also not exactly DC. So what we have the next is the full wave rectifier. In the half wave rectifier, the discharging time was more, so the capacitor was discharging to much more value. In the full wave rectifier, we are going to convert our input voltage to such type of voltage. Whatever we had at the reverse axis, that we are bringing to the positive axis. So the average is doubled. In the full wave rectifier, the average is doubled. So there are two types of full wave rectifier. One is the bridge rectifier and the center tap rectifier. So we are talking about bridge rectifier over here. So in the bridge rectifier, this is a kind of bridge. There are 4 diodes. These diodes are connected, 2 of them, which are in opposite branches, are in the same direction, and other 2 are in other 2, those are varying, those are in the opposite direction. For example, D2 and D4 here, even if we are opposite, these are opening in that direction. Yes. So now let us discuss what is going to happen. So what's going to happen? Just whenever we had the 7 volt. Let's consider this is which type of diode is this? So this is going to support it. We have it. So this is going to oppose in this way. The battery is going to oppose this, right? So we have to make this will oppose. If I am making this is connected in this way, negative is connected to the positive of it. It means this is going to oppose, and likewise we will be doing it for all. So the input is coming. The input is going through. If we are talking about positive cycle, the input will follow this path from this. Then this is the ground. Okay. And this was the negative side. Negative means it should enter through the N type. So N type is this. So through this, and then it is connected to the load. So this is also ground. This is also ground. You can connect both. So this is the complete path, and you can take you see here, and this is the path with battery. If we talk about the next cycle is the negative cycle. In the negative cycle, I can make it negative and I can make it positive. So in that case, negative is connected to positive with this type. Now, this thing going happen, and this current is flowing from this to this, and then it is going over here, and from here it is going to this, and then it is going to reach over here, and here this is connected then. You can see over here this is negative. So this negative is appearing, and the bottom side is positive, that is appearing directly over. The previous cycle also the polarity was seen. What is the polarity was seen? So it's shown over here that the positive cycle will be getting, but the output will be getting. This output we are getting in this way. We are getting both of these cycles as positive. The previous cycle this was positive over here. So this was open. Right? It makes only output connect. Both of these we have to the side, and as I told you, because every time this is V gamma voltage away. So V gamma and V gamma, how much you are having? So the difference over here is twice of V gamma. There are two diodes, so V in minus twice of V gamma. This is what we will be having at the output, because there are two diodes. So if you have any questions so far, please feel free to ask. Any question? Do you have any questions so far? Please type in the chat box if you have any question. You may type Y or N in the chat box if you have any question. No questions. Very good. No, very good, very good. So let me take, there are 10 more minutes are there. Dr. Geeta, can you hear me? Dr. Geeta? So we have 10 more minutes. After that, there is another lecture that is by Professor Gaurav Datta from IIT Kharagpur. He will be taking the next lecture. So in this, let us take the next diode related applications. Whatever 10 minutes are left, whatever I will be able to cover, I will be taking them. So these slides I have taken from Volistep. So for all the teachers, let me tell you, there is something called as teachers resources. So the slides you can get along with the books in that category. You have to register in that. For example, this is from Pearson or maybe Cambridge, Oxford, or some other publisher. Whatever book you are using, you tell that you are the madam. Have you tested the connection with Professor Gaurav Datta?
No, ma'am. Actually,
Dr. Geeta, have you tested the connection?
No, ma'am. We don't test the connection. He has to register and join. That is the thing. Like if he joins, we'll make him as presenter. Is he?
Yeah. So first of all, there is something called as load line analysis. What does it mean? There is Q point. Q is the operating point. So many times I found the students are actually afraid of this. Why these are afraid of this? Because this is not covered in good manner. So what exactly is the load line concept? Basically, you have a diode or any kind of circuit you have. That circuit, I have taken very simple circuit. In this, we have to determine where the diode is operating. We know that this is the diode IV characteristics, right? Forward bias and reverse bias. Now I have some input voltage V and I have some load resistance R. Okay. Now what is the current? Current is V in upon R plus RD, diode resistance. Now in this, basically out of whatever you had the IV characteristics, where it is going to land. So there are two conditions. The resistance will follow the Ohm's law and diode has the characteristics. So whatever resistance is going to follow. So resistance is going to follow if V in was there, then V in upon R, that was the current flowing through this maximum amount of current. So you can see over here, this is the maximum amount of current. V is the input voltage divided by R. That's the maximum amount of current. And then minimum amount of current, how much it can be when it is shooting up maximum, means the diode is open circuit. What it can be? 0. The current can be 0. But what will be the voltage at that time? VD voltage, that is the maximum voltage, right? So we have drawn a line for the resistance, for the maximum current and minimum current at the current and voltage axis. That is simple Ohm's law using the resistance and the voltage given. So this first line, this line is actually for the resistance you have to draw. And the second is the IV characteristics of the diode. These are the characteristics of the device. It is not only for the diode, it can be any device. It can be your Zener diode, it can be your BJT, MOSFET or any device. What you have to do, if you have two unknowns, it means two things are actually there to help us. So one thing, Ohm's law is there to help us, and other thing is the IV characteristics of the device. Wherever both of these are coinciding, that is the solution. Means here your device is operating because it has to satisfy both of the conditions. So this is the load line concept. Okay, this is the load line concept. It has to satisfy both of the conditions of this resistance and this is from the device. So if it is going to meet both of these curves are going to meet, that is your Q point, that is your point where your device is currently operating. Now what is going to happen if I am going to change the resistance? If I am going to change the resistance, let's say I am increasing the resistance. So the resistance is increased, so it means the current is decreasing. So the current is coming from where here? E by R. Increasing the resistance, current is decreased. Now when the zero current is there, the voltage will remain same, right? So it means the straight line will touch in this way. So the Q point is being shifted over here. Wherever both of these are cutting, there the Q point is being shifted. And this is how the load line concept and the load line analysis is done, that where your device is operating. So for actual devices, you have to figure out where your device is operating. For example, you are going to do the circuit analysis. In those circuits, you have to find out, for example, BJT related current equations you will be writing, MOSFET related, and other equation will be for the from the KCL or KVL of the loop. So that is there to find out the operating conditions where your device is going to operate. That's the concept of the load line. Okay. So this is the forward bias and the reverse bias load line concept I have covered. So let me take it. So let me directly cover to diode clipper. What is clipper? Clipper is the circuit which is going to clip away. Clip means remove. Unwanted portion removal is clipping. So half wave rectifier is a clipper. Right? So this is a circuit of half wave rectifier. In this you can see that the negative portion from the circuit, the waveform is vanished away. This was the negative portion from the circuit, and then this is vanished away, and this will be the output. So this is the clipper. If you want to change that from where you want to clip it away, so you can apply some series voltage. So this series voltage, just have a look. This 5 volt positive is connected to positive of the diode. So positive connected positive of the diode, it means it is going to support the diode in the forward bias. If it is going to support in the forward bias, it means what? Your diode becomes on, right? At early stage, when this was 0, so it started on. So basically, your diode is on. You will be writing Vi plus 5 volt minus V gamma. You have to write. So here the diode has been taken as the ideal diode. So in ideal diode, there is no concept of V gamma. Otherwise, being an electronics or electrical engineer, you have to write it in this way, that it is going to be plus 5 volt and minus V gamma, because that is the voltage offered by the diode. what you have to write. So this is going to be 5 minus point, let's consider it silicon diode. So 5 minus this value, this is going to give you 4.3. So it means 4.3 is the value with which it is actually already it was on. So it means it is going to turn on somewhere here, 4.3. Instead of 5 volt, make it minus 4.3, right? It was already on. At that time, it was already on, right? So it means the negative portion is lesser. So that portion where diode was off, that is flipped up. Okay? If you are just reversing the supply, let's say I am going to make it reverse, 5 volt. What is going to happen? This 5 volt is opposing the input. So the total it becomes this 5 plus 0.7. How much? 5.7. So how much portion you will be having? The portion 5.7 is flipped away. This is, let's say, 5.7. So you will only be able to see this portion. Above 5.7, whatever you have, that portion is visible, right? So this is the only portion which is going to be visible to you if you are having, you are reversing the supply. Okay. Now another category is the parallel flipper. You can interchange the resistance and the diode. So when you are going to interchange, the whatever portion was flipped away, that portion actually is appearing in this case if you are interchanging the direction of resistance and the voltage. Okay, this is the summary of all types of flippers we have. This is the summary. So I will upload all the PPTs today. Yesterday I was a little late because of some prior commitment. So I am going to upload all of the PPTs by today. And this PPT is online available, so there is no need to upload. I have taken it from Pearson and it is available in the public domain. And it is covering all the applications related to it. So let me type the this PPT in the chat box I have shared. Fine. Dr. Geeta, can you hear me? Dr. Geeta?
Yes, ma'am. I just spoke to sir. I am sharing the link.
So can I stop it now? And because you will be switching the session, right?
Yes, ma'am. We will change the session. Give us 5 minutes. By the time I think sir also.
Okay. So dear participants, the next session, if you have any question, you please keep on typing in the chat box. I will be taking the question. And let's wait for the next one. Yeah. Yes, please, ma'am, you please switch to the session.